right, good morning, everyone. This is Monday, March 30th. This is Biomechanics, okay? KNES 415. If you are in KNES 310, you are in the wrong video. Stop commenting on a video that I know you didn't watch because you're not in this class. Oh, y'all, and be careful. Mardi Gras. April Fool's is coming up. It's gonna be a bad one. So just be careful. Mind your false news, because there's a lot of people and they bored and they're gonna come up with some crazy stuff. So just be careful. I'm gonna get to today's code word in a little bit later in the lecture. So alright, so let's do this. Today I am going to first lead off with the concept of scalar and vectors and why we have them, and then I'm going to segue that into kinematic variables and definitions. Now, it's important to know that on your test, there's going to be a lot of definition questions or matching terms with what they mean, especially in the physics part, okay? So, in other words, if I lecture about impulse, momentum, velocity, acceleration, different force variables, the key thing is going to be to know what those things are. And to make sure we're all on the same page, what those things are going to be based on how I define them. Not that I invented them, of course not, but we're going to try to use similar verbiage so that we're all on the same page. That's all I'm trying to say. So we're going to use our verbiage in class to make sure there's keywords that you guys know to look for, or to clarify the difference between this versus that. So keep in mind that our verbiage is going to reign supreme, but it's just so that we're all on the same page for the test and there's no miscommunication. So why do we have vectors and scalars? And one of the reasons, well, first of all, what is the difference? And the difference is direction, okay? So scalar is a variable that only has a magnitude to it. How much, that's all that matters. And a vector has direction to it, okay? And sometimes it's not enough to just have an amount. You got to know where it's going. I'll give you a practical example, a real life example, okay? $200 is just an amount of money. And to give it purpose, we have to give direction to it. Meaning, I owe you $200 is a different direction versus you owe me $200. You see how that switches the direction? I owe you versus you owe me. Or think about if you write a check for a bill, right? The magnitude is $200. The direction is who's writing the check. And when you give that check to someone, you lose negative 200 and they gain positive 200. So that positive or negative is the direction of that money, okay? Direction also matters in other variables, like distance versus displacement. I'm going to define those in a little bit, but I want to give you some context to these things, okay? So let's say we have X and Y. So let's say this is see if I could do it like this, guys. Okay. See if I can do it like this. So let's say I have, let's say we're going somewhere and we walk a path. Let's say this is a GPS. And so, you know, some fancy apps you can look and see where you went, right? So let's say we go here and then we take a right-hand turn and we go there, okay? Obviously social distance walking, you're not going to visit anybody, right? But we can look at this in two different ways. If you went down the road here and then you went up the road there, we can say, what is your distance? How far did you go where direction didn't matter? And when direction doesn't matter, it's kind of like, you know, how the crow flies. You ever heard that phrase before? So how far did you go, right? So if you go here and then there, you know, how far did you actually end up going? This. So how far did you go? Or you could look at it, how far did you go counting your steps, right? Or counting your miles. So if you were counting your miles, it would add up this plus this. So how far did you go can kind of be, you know, there's kind of different answers. How far did you go as the crow flies? Well, then that would be from here to there, because at the end of the day, you started here and you finished there. That's how far you went. But you could also look at how far you went is like absolute. How many steps did you take? How many miles did you walk? And that would be this minus this. So when direction matters, okay, let's pretend this is a standard compass, north, south, east, west, okay. So now we can say, how far did you go east? Now that adds direction. How far did you go east? None of this matters to how far you went east. Does that make sense? So in other words, if I walked east and then took a right-hand turn and went north, I didn't go any further, I didn't go any shorter. So direction matters. Now, when I take a right and I go north, how far did I go north? If I only look at as the crow flies, from point A to point B, my displacement, how far did I displace? East and north is blurred, is combined in this path. So in other words, let's pretend instead of walking here then there, let's say I'm at a park and I have the choice to walk this path, okay? So on the road, I gotta go here first. All of my movement is east, none north. Then I take a right. All of my movement is north with no east. But if I'm at a park where I can do a combination of the two, northeast, I need you to see that north and east is blurred, it's combined, I'm going north v east at the same time. So therefore, I kind of have some of both taking place. So sometimes when you have these combinational things where some of my motion is in a combination of direction, there's going to have to be tools that I can extract. You know, let's say this was 1 mile. I walked 1 mile, but I had a combination of east and north happening at the same time. I'm going to need a tool to be able to extract. Do you remember Mickey Mouse Clubhouse? Oh, toodles. I'm going to need a tool to extract how much of that walking was north, how much of that walking was east. And ladies and gents, that's what trigonometry is. Trigonometry is the relationship between angles. I could have a steeper angle or a more shallow angle, and the sides that have to come about because of those angles and those vectors. So that's all trig is. Trig is the tools we use to answer a kind of simple question of, well, if I'm walking in a combination of directions, I need a tool that can tell me at the end of the day the so what's. How much of my movement was here? How much of my movement was there? Okay? So get ready. Trigonometry is coming. But trigonometry can be super easy if we remind ourselves why we need it. And that is to, in biomechanics, extract combinational vectors, magnitudes that have direction. And when we have magnitudes that have direction, like forces and velocities, it's more common that those vectors are going to be in combinational directions. If you think about it, it's ridiculously hard to apply all of your force perfectly in one direction. If you have a 360-degree window of opportunity to apply a force, you only have 4 spots where all of it is in one direction, right? Positive x, or east in this case, negative x, positive y, negative y. In other words, you have infinitely many more chances of having a combination. And so we need a mechanism in place to say, all right, how much of that force was in the up-down direction? How much of that force was in the across direction? How much of that force was in the front-back direction? How much of that motion was in the up-down, the left, right, the front, back? Knowing full well that majority of the time, that motion or that force is going to be in a combination, okay? So vectors and scalars, how much and how much in what direction? For forces, the kinematic stuff, forces are vector quantities. Direction matters. In the real world, you see this all the time. Direction matters. When you go to push on a car that's run out of gas, direction of your push matters. It's not just push the car. It's we're going to get in the back and push it in a certain direction. Direction matters with your forces. If you've ever corrected someone's form or mechanics while they're doing a lift to keep them safe, that's all indirectly about direction of their applied force. Direction matters with forces. So forces are very vector. What are some scalar examples where direction doesn't matter? Distance is a scalar. How far did you walk? Remember, you can walk in a circle around a track and travel. How much did you walk? I walked 10 miles around the track. And when you take direction into account, then you can say, well, when I'm on this part of the track, I'm walking west. Then I curve, walk less and less and less west, more and more and more north. Then less and less and less north, more and more and more east. Less and less and less east, more and more south. Less and less south, more and more west. Okay. Time is a scalar quantity. That's kind of cool. Mass is a scalar quantity, and I'm not talking about this. I'm talking about the concept of how much stuff an object has. You guys know that as inertia. In other words, the amount of stuff that this baseball has is irrelevant of direction. It doesn't matter where it's moving, it doesn't matter. And remember, it can't apply a force to itself. So the concept of mass is a scalar quantity. That's important to remember for a later equation that we're going to talk about. So, for the purposes of biomechanics, the scalar quantities that are going to be important to us is mass. Distance is a scalar where direction doesn't matter. It's just how much, how far did you walk, how far did you run, how far did you drive. So in other words, your speedometer on a car, not your speedometer, your odometer. It has how many miles you drove. There's no direction to it. It doesn't extract. You went so many miles north, so many miles. There's just the total number of miles. It's just a magnitude. Speed is a scalar quantity. How fast are you going where direction doesn't matter? So you think of, for instance, let's say you're traveling on a road that's northeast. You have your GPS on, and it's saying you're going northeast, and you're going 70 miles an hour northeast. Scalar is just how fast are you going. Vector would be how fast are you going east? How fast are you going north? See, those are two separate things. Because if you're moving in a combination of north and east, not all of your motion is north. Some of it is here, and some of it is there. So that's when direction matters. And the reason direction matters is in biomechanics, we cannot compare apples and oranges. Well, yeah, we can. They're both fruit. You know what I'm talking about. So my point is that in Newtonian physics, it's Isaac Newton physics, and I'm trying to relate this in common terms. X forces that are in the east, as my little example, X forces can only influence X motion, or another way to look at it is across forces can only influence across motion. I can't push this ball across and make the ball go up. Now, if I give it some up force, I can influence the ball in the up. But it should make sense that if you had a chair and you applied an X force to that chair, the chair isn't going to go up and down. You have to apply an up-down force on the chair to make it go, oh my gosh, Mama Kitty, you being silly. So that's important. X forces, across forces, influence across motion. Y forces, up-down forces, influence Y motion. So since these types of forces don't influence this type of motion, when you have forces that are at angles, that are combinations of X and Y, then I have to say, I can't just take that 200-pound force and apply it to both this direction and that direction. I have to take this 200-pound force and separate it into its vector components. How much of that force is trying to influence the ball this way? And how much of that force is trying to influence the ball that way? Because only this vector can influence the ball in the up-down. And only this vector can influence the ball in the left-right, or the across. Now, the combination of this plus this influences the ball this way, right? But this force and motion is in here plus this at the same time. So vectors for us is going to be all about X and Y components of whatever we're talking about, whether it's forces or the subsequent motion variables, okay? And what ties this all together is the trigonometry. We're going to get to that this week. Maybe I'll do that one on April Fool's lecture on Wednesday, okay? All right, let's get to the confirmation word of the day. So what I'd like for you guys to do today to confirm that you watched this lecture, I'm not done with the lecture, so don't go anywhere. I want you to put the word watched, but I want you to put a period after the D. Just a small little period. Watched. So not an exclamation point, just a little period. Watched, period. And I'm going to look for that period, and I'm going to see if you really watched this lecture or you just put always love the people that put watched and then like 10 exclamation points, like, yeah, I watched it. So, vectors and scalars. Let's get into kinematic variables. Kinematics is dealing with motion. So, objects' motion and kinematic variables. All motion concepts start with a very simple question. Location, location, location. It's like real estate, right? 3 things about real estate: location, location, location. Where are you at? Where is this ball? Now, you can give it some, GPS, global positioning system. That's where are you at? And they can tell where you're at, and they use things like latitude and longitude, remember, like on the globe, and they can track your 2D position. If we want 3D, then it's like, where are you at? On the up-down, right? You can add the up-down to that. In other words, you could be on the 5th floor of a building. So now it's where are you at this way, and this way. If you're on an airplane, right? Where are you at latitude, longitude, and altitude? Now, don't give me no attitude. Dad jokes, all right? So where are you at? Where's this ball at? And our body's, man, so cool. We use context clues to see things in 3 dimensions. So things like this ball shadow. You don't think about shadows, but you use shadowing to help you get third dimensions, depths. So I can look at this ball and how it's in the air, and I can say, where is this ball at? And I can place it, I could put its position relative to other things. So like for me, it's about, maybe a foot away from my face. It's, maybe about 4 feet off of the ground. It's about 5 feet from the wall. And I use these concepts of relative, that's not Einstein's relativity, but putting the ball relative to other objects that I see in space. And its movement can be used based on its change of position. So the first definition you're going to have to know is position. Where are you at? And I'm going to use a very common test to explain or give examples to all of these kinematic concepts. But let's assume we are looking at kids doing in track 100-meter dash. Now, 100 meters, I know in America, we use yards a lot. Well, yards. Back in the day, they used to 100-yard dash, 400-yard, not 400. Doing the 40-yard dash, right? It's all yards, and yards is just there's 3 feet to a yard. So 100-meter dash, 100-yard dash, 40-yard dash, it's all arbitrary. We're going to do a 100-meter dash. No, you know what? I changed my mind. Let's do the 40-yard dash since it's in yards, and I could use feet in yards. So 40-yard dash is the test, and 3 feet to a yard. So you're looking at running 120 feet. Okay. So let's think of now kinetics, forces. Well, intrinsically there's muscle forces that are pulling on bones, and extrinsically there's the ground or the turf pushing you back, and gravity's pulling you down. But that's not what this conversation is about. This conversation about is your motion. So notice when you're testing a lot of people on the 40-yard dash, everyone's position is the same. The starting line or the starting point, the starting position, it's a place where everybody is going to be the same. Your position is the same. So let's think about this test in a different way. Where are you at? That's a position question. You call someone on the phone and you say, hey, where are you at? And they're like, I'm at home, Couillon. Where are you at? You're supposed to be home. Get your butt home. Where are you at is a position question. And The object they're talking about in the case of where you at is you. You were an object, okay? Objects have stuff, have mass. Where are you at? So at the 40-yard dash, where are you at is the starting line or the starting point, okay? I'm gonna put a little, I'm gonna try to draw, wee, look at my awesome artwork, okay? Starting, that's your position. Now, you start and then you finish, right? Now, what's cool about where you finish is that you keep running, right? So I'm gonna draw a little picture of my little man running. Whee! Some wind blowing. Right? So start, now you see that finish line? That's a position. That is a point. And start, finish. And even though I run past it, none of that matters. Right? I keep running out the stadium, keep running out the gym, keep running out the track. It doesn't matter. My test stopped when I reached this other point, this other position. So the 40-yard dash isn't necessarily where you are. It's where the starting line is and where the finish line is, and how you change positions. You go from here to there. Change in position is a concept. That's what we call distance if there's no direction to it, and displacement if there is direction to it. Let me give you a football example of the difference between the two. If a running back gets a handoff or a pitch and the running back runs to the left and changes direction and runs back to the right, runs around, the running back could have ran 30 yards of distance. But what does the running back get credit for? Direction. How far did you run that way? Or how far did you run the opposite way? So in other words, if the running back ran 30 yards, but he only ran 3 yards forward, he only gets credit. His displacement was directional. You only get credit for how far you ran in a certain direction. The side to side doesn't matter. That matters. And this doesn't matter. It's only in that direction. So displacement is going to get you the first down or lose yards. You see how that works? It doesn't matter your distance. It's your displacement. Okay? So change in position. Now in physics or biomechanics, we denote change with a delta, with a little triangle. Okay? So if we have P, little p is position, delta P is change in position, and that's another way of saying distance. Or displacement. And displacement is a vector quantity. And what we do with big D is displacement, little d is distance, we put a line over vector quantities. So we put these little lines over them, velocities and forces. We put a little line on it to remind ourselves that a direction matters here, okay? So what's the point the point is very important. We're working our way towards all of our kinematic concepts, and I'm trying to define them with practical examples. So let's pretend you were running a 40-yard dash. Okay, start, finish. And let's say you drifted. So in other words, you're running and you kind of swayed over to the side. So in other words, you might have ran 40 yards before you actually crossed the finish line. But that time ain't gonna stop until you went 40 yards that way. In other words, even if you drifted to the side, you don't get credit for any of that stuff because direction matters. So a 40-yard dash or a 100-meter dash is a great example of displacement because direction mattered. It didn't matter that you just go 40 yards. It matters that you went 40 yards that way in a certain direction, okay? So distance, going back to our original so how far did I walk? If I take this route, this would be my distance because direction didn't matter. This would be my displacement where direction mattered. I walked so many miles east or in the positive X, and then I walked so many miles north or in the positive Y. And when you make things vector, then you can add or subtract. So you can compare apples and oranges. So, and that's with forces or velocities or displacements. Okay, so the concept of vectors is that you can do something with it. You can balance your checkbook. Okay, well, think about it. Let's say you have a couple and they have two separate bank accounts for whatever reason. Let's say they have a business together and they have, because maybe one is like the CEO and has more job responsibilities, so they get in a check that has just magnitude to it, and they have to give each other direction to split it into their separate bank accounts. So, let's say it was a 70-30 split. So you take the amount, you extract how much she gets the 70, and then he gets the 30, and then once you extract who has what, then you can do something with it. You can make the deposit. Because you extracted what's his and what's hers. What's hers, what's hers, what's his, what's his. The point is that you took it and you extracted it, and now you could do something with it. And so that's the same thing we do with forces and movement variables. A lot of times there's combinations to these forces and movements, and so we have to extract what's in the up-down, what's in the across, what's in the depth. We got to extract them into their vector components so then we can do stuff with them. Like add up the forces, add up the motions, cancel out the motions, cancel out the forces. But we can't do anything useful with Y forces and X motion because Y forces don't influence X motion. X forces influence X motion. Y forces influence Y motions, okay? So you have distance and displacement. Now, you think about a test like the 40-yard dash, and what is it a test of? Speed, right? But yet we only report it in time. So we're going to change position, start, finish, and then we're going to measure how much time it took you to do it. So change in position, as I told you, is distance. Directional change in position is displacement. When we add the element of time, we infer this new concept called speed, okay? Over time. Speed. Distance over time is speed. Displacement over time is velocity. So let me start over. So distance in regard to time is speed. Okay. So d over t is speed. What does that mean? What does speed mean? Another way of looking at speed is how much time did it take you to displace? So if I know I'm going to go from a position of 0 to a position of 40 yards away in a certain direction from 0, I displaced 40 yards. I traveled 40 yards. How much time did it take me to do it? So your distance or your displacement, if we're vectoring, is going to be at the top. And then how much time did it take you is going to be at the bottom. How much time did it take you to distance? Or how much in terms of velocity, it's going to be how much time did it take you to displace? Let's think about it. If everybody is distancing, social distancing, anybody? If everybody is distancing the same, in the case of running this race, everyone distances the same, 40 yards. Then variations in this will infer variations in that. We do physics all the time in our heads, and we don't give ourselves credit for it. Because people that run races don't report how fast they were running. And we know it tests speed, but no one says, how fast was Usain Bolt running? We don't give it in terms of speed. We just know that if this number is lower, they were running faster. Because we actually did physics concepts. We know this is the same for everybody, so variations in this is going to infer variations in that. The smaller this number, the bigger that number. If everybody is displacing 40 yards, and I did it in less time, I did it in 4.5 seconds, and you did it in 5 seconds, my lower time infers faster speed. Okay? So speed is displacement in regard to time. Or if we want to read it in reverse, how much time did it take you to distance, or how much time did it take you to displace? Okay, that's what speed is. Think about your odometer, your speedometer, sorry. Think about your speedometer, 20 miles an hour. You go 20 miles every hour, distance over time. 40 miles an hour, distance over time. 60 miles an hour, distance over time. And we infer speed from that, right? In other words, if I go 20, and here in terms of your speedometer, what's the constant? The constant is time, 1 hour. Time is the constant. So changes in this, once again, infers changes in that. If I go 20 miles in an hour compared to 40 miles in an hour, well, if I go farther in the same amount of time, I had to be traveling faster. That's all it is. A lot of this stuff is common sense when we put it into terms that we know and understand, okay? So to summarize today, I went over vectors and scalars. I introduced you to some kinematic concepts, position, change in position, and then how much time did it take you to change position. I'm going to end on that because when we move up to the next question, how much time did it take you to change speed, it kind of starts to get into the rabbit hole anymore, but it's still super simple. I'm going to give analogies to help you out, okay? So remember, the key word for today to confirm is watched, but you got to add the dot, add the period after watched. Watched with a period, and I'm going to look for that period to confirm that you really watched this, okay? All right, guys, y'all have a blessed day, and I'll see you on Wednesday. Don't forget about it.